FC Star, a hybrid flying and climbing sprawl-tuned robot. A presentation and brief summary of the abilities and technical aspects of the robot. This presentation will have the following layout: a brief description of the robot, kinematic model of the robot, path planning of the robot, control systems of the robot, operating in non-ideal environments, and advantages of the robot structure. The robot is composed of a main body, left and right arms, 4 propellers and wheels, the central controller and its battery. The central body contains the battery and the controller for the motors. The servo motor, which can vary the sprawl angle of the arms, is contained within this component. If the flight controller reads that the robot is perfectly level and facing forward, then the central body is perfectly level and facing forward. 2 arms are attached to the body by hinges. The angle of these arms are controlled by a servo motor on the central body. The arms can vary between 0 degrees, as shown in the diagram on screen, to 45 degrees, as used when driving. The arms contain the belts used for distributing power from the back motors to the front wheels. The arms also feature the gearboxes used for gearing down the speed of the motors so that they can have the greater torque needed for driving. The gearboxes are only on the back half of the arms, since the output shaft of the motor feeds directly into the input of the gearbox, and the output of the gearbox is directly coupled to the back wheels and the belts. The arms also feature a bearing that keeps the belt further away from the ground so that the robot can have greater clearance when driving. There are 5 main actuators on the robot. There is a servo motor used for controlling the sprawl angle of the arms of the robot. There is also the 4 motors used for driving and flying. The motors are connected to a 20-to-1 speed down gearbox to modify their speed and torque to drive. Only the back motors are used for driving, so that the front motors can be used for providing additional downward force as to make the robot able to ascend slopes with gradients up to 90 degrees. The robot has 4 propellers directly attached to the motors, enabling it to fly like a regular quadcopter. The propellers are uniform such that they produce the same lift either up or down, depending on the direction of rotation. There are 4 wheels connected to the robot, enabling it to drive. The back wheels are connected directly to the output shaft of the gearbox, while the front wheels are connected to a belt driven by the output shaft of the gearbox in the back. The wheels have rubber tracks to provide greater friction between the wheels and the ground. This is especially needed since the wheels are at no point perfectly incident with the ground. Driving. By using the 2 rear motors, the robot is capable of driving on the ground. When in driving mode, the back 2 motors pass their torque through a 20-to-1 gear reduction box which turns the back wheels directly and the front wheels via a belt. There is an acetyl idler which keeps the belt further from the ground. Since there are only 2 motors controlling 4 wheels, this may be referred to as tank drive or differential drive. The robot may take on any sprawl angle of choice while driving as long as it allows the wheels to make proper contact with the ground. As stated by the designer, in drive mode, the robot can reach a top speed of 3.2 meters per second and is capable of moving a wheeled payload of 40 kilograms. When the sprawl angle is set to 0 degrees, the robot is capable of acting as a regular quadcopter. In this mode, the wheels play no part in the robot's motion, but they are still in motion since the wheels are not disconnected from the belt system. The robot features an Airbot F7 flight controller to take measurements needed for flight control and stability within the air. The flight path is controlled by the user, but the specific speeds and currents sent to each motor is controlled by the flight controller and the control system within the robot. By using the front propellers and with motors with opposite direction to that in flight, along with the regular driving function of the robot, the FC Star is capable of driving on walls and extreme slopes. The front propellers are capable of generating enough negative lift that the robot can create a great deal of normal force to hold itself against a wall. For the FC Star, there are 2 kinematic models, one for flying and one for driving. The kinematic model of the flying robot is not discussed in the paper, but the model of the driving robot is. As seen in the free body diagram on screen, the robot's center of gravity is in the middle of the center body component, and the global frame is assigned from the center body. The flat XY plane is taken as being parallel with the top surface of the robot, and the positive X direction is given as taken from the front of the robot. For a given slope angle lambda, the components of its own weight combined with the negative thrust provided by the front propellers must be able to create a strong enough frictional force as to hold the robot to the slope. Since weight and normal reaction force of a body is a factor of the frictional force experienced by the body, in this case the wheel, this model proves that for a given slope angle, there exists some thrust force F and sprawl angle ρ that provides enough downward force as to make the robot able to climb the slope. In addition, since the robot can ascend a 90-degree wall, this tells us that the robot can produce enough downward force as to create frictional force great enough to hold the robot in place on that wall. The robot is entirely controlled by a human user. The only function that is not controlled directly by the user is the stability control for flight. This is done by the flight controller and takes readings from the gyroscope to correct itself. It does not feature any extra sensors to prevent collisions, nor does it have any added functionality to return to any location. The servo that controls the sprawl angle located on the top of the robot has its own controller built in for moving at fixed angles, so a separate control system is not needed. The four other motors used for flying and driving do not have controllers built in, and they require their own control system. Just like how the robot itself has two modes, flying and driving, the control system has two modes with the same name. The overall structure of the control system is shown on the screen. When in flying mode, the inputs to the motors come from the flight controller, which takes inputs from its own sensors and the input from the main receiver, which comes from the operator, to supply current to the motors to guide its path accordingly. When in drive mode, the motors are disconnected from the flight controller, and the back motors receive input directly from the receiver and by extension from the operator. In drive mode, the back motors can allow the robot to drive around, while the front motors are set at a constant speed by the operator. They can vary the duty cycle of the rotation from 0 to 100. In this drive mode, the front motors spin in an opposite direction to when in flight mode. The question arises, if a robot can fly, what does it need to drive for? This is a good question, and this robot provides a good solution. While driving, as opposed to flying, significant battery power is conserved. In an ideal environment, the user will be able to charge the robot often, so any consideration for preserving battery life is a positive. With the ability to change the sprawl angle, the robot is capable of getting into areas with low vertical clearance. This is useful if the robot needed to deliver a payload underneath something, such as a collapsed building. This can be combined with the flying mode to work as a specialized surveillance drone. In situations where the robot cannot fly, the climbing mode provides a good alternative, such as in an area where the robot is to not make much noise. The robot could climb up a wall instead of making the full noise associated with quadcopter flight. Additionally, there may be scenarios where flight is not possible. This may be due to wind restrictions or within a restricted airspace. The same can be said for driving. There may also be scenarios where driving is not possible but flying is, such as over water or in mud. This robot, if it was combined with a wireless camera, would be specially suited for search and rescue operations in areas deemed unsafe for humans, or surveillance operations where the robot would attempt to keep itself concealed. The robot's unique sprawl feature allows it to accomplish two main things. It can convert itself between a regular quadcopter and a driving vehicle. It allows the two modes of driving to only use four motors for motion. This is a special advantage due to the fact that the robots of this kind usually require extra motors and treat the two modes as separate. By repurposing the motors, weight is conserved, thus improving the flight functionality. Additionally, the option for using negative thrust to enable climbing is realized by using this sprawl feature. The FC Star robot is capable of driving, flying, and crawling on walls. It does this by taking advantage of 5 actuators and the fact that this body can change. It can operate as a regular quadcopter as well as a driving vehicle. It can ascend steep slopes by using its front propellers to produce a downward force. This robot can see numerous benefits to society depending on its use in either payload transportation or attaining information where humans cannot go. Additionally, it is rather appealing to look at.